All right, everybody, let's learn about drawing Lewis structures. So Lewis structures are a way in which we represent the 2D picture of covalent bonds. So ionic bonds are always that positive, negative pattern, right? So they all look about the same. Metallic bonds are always the electron C, and so they all metals and all ionics look somewhat similar at the molecular level, but covalence can vary a lot because of how sharing works. So remember, in a covalent bond, the atoms have high electronegativity, so they're not going to give up their electrons, and they are trying to complete their octet. So these ones both have 7. So to achieve, it's I'll share with you, you share with me. It gets shared between the two of them, and so now they both have 8. If they both share 1, it's called a single bond. Down here with our next example, carbon dioxide, we have an example of a double bond where they're sharing twice. These bonds can be represented by the dots in between or by lines. You'll see I prefer the lines. I just think it looks cleaner, but technically the dots are a valid way to show it as well. And then you can even have triple bonds. Okay. These are the steps we're going to follow when drawing Lewis structures, and then we'll do some examples once you get this filled in. So key thing here is it's all about valence electrons. We take into account how many they each come with. If the molecule has a charge, we need to make sure we add or subtract the number of electrons. We only start with single bonds first. Don't do double or triple, only if it's needed. Keep in mind the goal is to achieve an octet, and you always focus on the atoms bonded to the central. So I think work outside to inside. Okay, is how you all should look at your model. Okay, all right, let's give it a try. Okay, so we got PCl3. So I'm going to always start, so kind of read it left to right, where the furthest to the left is majority of the time going to be the central one. So I'm going to P in the center, and then I have 3 Cl's around it, okay, because of the formula here. Now, I could have put the Cl up here instead of down there, wouldn't have mattered. We typically always kind of put it in like a plus shape pattern, but if you don't have 4, where it goes in that doesn't matter, okay? All right, if you look at the periodic table, should have put one on here, but let's draw a quick rough model to remind you. Okay, so the column number tells you how many valence electrons they have. So if I look on there for phosphorus, it's in column 5. Remember, we skipped the D block. Okay, chlorine has 7. So I'm going to put 5 dots around my phosphorus. 1, 2, 3, 4, 5. Then I'm going to put 7 around each of my chlorines. 7. Okay, keep going here. Like so. Okay, so start with valence electrons. Then, remember, we work outside ones first. So looking at this chlorine here, it has 7 valence electrons. So to achieve its octet, it only needs 1 more. So we're going to bond it there. Okay, by doing that, these all now belong to chlorine, so it has 2, 4, 6, 8, and it's good. So each of the chlorines, because they're all the same, will also do the same, giving this one its 8, this one its 8. All of the outside ones are happy. So now you can look at your center one, but majority of the time, it's just going to do whatever it did. In this case, we do have 2, 4, 6, 8. And we're done. So there's our structure for PCl3. All right, let's do this one. So in this case, our first one, if we're looking left to right, is H, which can never go in the middle because it only has 1 valence electron, and so it can't bond more than once. So then I'm just going to move to the next one and put carbon in the middle. So we have carbon, put hydrogen over here, nitrogen over there. Hydrogen comes with 1 valence electron. Carbon comes with 4 valence electrons. Nitrogen comes with 5. Work outside to inside, so hydrogen has 1 and it only needs 2 total to fill the inner shell. So we just do a single bond there. Nitrogen comes with 5. So to get 8, it's going to bond 3 times. So we're going to go a 1, a 2, a 3 and make a triple bond. Check the center. Carbon. Carbon, in this case, has 2, 4, 6, 8. Everyone's good. And we're done. Now, if it was an FRQ, I would maybe quickly redraw my structure to clean it up, like so. Once again, just to make the triple bond a little less wonky, but technically this is correct in having all the right pieces. All right, let's try another one. Okay, we got BrO3 with a minus charge. Okay, so I'm going to start with bromine, and we'll put that in the middle. And then we got 1, 2, 3 oxygens. Bromine has 7 valence electrons, so let's add 7 dots to that. 1, 2, 3, 4, 5, 6, 7. Okay, our oxygens are all coming with 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Okay. All right. Now we do need to take into account this time our charge. So this means here that we have an extra electron that belongs to the molecule as a whole. And so we need to add it to one of our elements. Now, similar to before, always go outside elements, not the central. So we're going to add an extra. I'm going to keep it red so we can just see the difference. So let's put it on this one. Once again, it doesn't matter where we put it, but I'll put it on that oxygen right there. Then I'm also going to put brackets and show where that extra came from. Okay, all right, let's go ahead and check our outside atoms and bond as many times as needed. So this oxygen comes with 6, so it's going to bond twice. Okay, oxygen up top right here also has 6, so let's do another double bond there. And then this oxygen over here, since it got the bonus, has 7, so it only needs to bond once. And there's our structure. Now, if you're curious and you're looking at bromine, it has 2, 4, 6, 8, 10, 12. So keep in mind, I'm going to flip back here. Okay, the central atom can have more than 8. There are some molecules that can't, or not some molecules, some atoms cannot go above 8, and we'll address those here in a second. But bromine is one that can, and it does. And so that's our structure in the end. All right, I want you to try this practice problem on your own, so go ahead and hit pause on the video. And then once you've had a chance to draw, hit play, and you can check your answer and see how your understanding is coming. If you get it correct, you can have a smiley face. So the correct structure you should have in the end should look something like this, where you have 2 single bonds and 2 double bonds. You should have brackets and your charge. Now, if you did your double bonds here and here, or here and here, like, it doesn't matter where at this case. We'll address the differences here in a second. Key thing is that 2 sides are double and 2 sides are single. Now, formal charge is a method we can use to check a Lewis structure and kind of prove it, I guess, to some extent. So it's a little equation we're going to use where we're going to take the number of valence electrons that the atom comes with. What I mean by that is it's not how many are shown in the picture, but how many it has. So like for oxygen, it would always be 6 because oxygen has 6 valence electrons. That's how many it comes with when it bonds. Okay, you're going to take that number and then you're going to subtract the number of bonds it has. Okay, or in a sense the line. So how many lines are connected to it in the Lewis structure. And then you're going to minus the unbonded electrons, which are, in our pictures, the dots. Okay, so it's valence electrons minus bonds minus lines minus dots is the way I think about it. Okay, now when we do this equation, what we're looking for is formal charges closest to zero. Now they won't always work out to be zero, but the closer they are to zero shows the stability in the molecule. If they're not zero, they should add up to zero or the charge of it. So if it was like our SO4 2 minus, the formal charges should add up to 2 minus. Okay. Now, when they're not zero, you want the negative charge to reside on the more electronegative atom. So remember our trend for electronegativity. Here's our periodic table again. That one was better than before. It goes like this. So the more electronegative atom should have the negative charge. Okay? All right, let's see how that works. So I'm given two structures here, and we're supposed to determine which one is the valid structure for CO2 using formal charges to support our answer. So I'm going to do each element individually. So I'm looking at this oxygen first. Oxygen has 6 valence electrons. We then minus the lines, so minus 2, and then we're going to minus the dots left on it, so this case 4. So the formal charge for this oxygen would be 0. Okay, all right, let's do our carbon. I'm going to just do it down here a little ways so we're not squished. Carbon has 4 valence electrons. We're now going to minus, we got 2 lines on this side, 2 on this side, so minus 4. And then there's 0 dots around it. And so it is also at a formal charge of 0. So looking good right now. Last oxygen right here has 6. Once again, minus 2 lines, minus 4 dots, 0. So as of right now, because we got 0, 0, 0, this in a sense proves, hey, this is not the right structure, and this is the one that is. But just to show you the difference, let's calculate this one really quick. So oxygen is 6. We're going to minus the 1 line, and then minus 2, 4, 6 dots. And so in this shape, this molecule has a minus 1 formal charge. Our carbon in the center still ends up being 0, but this oxygen over here ends up being 6 minus 3 minus 2, and so it's a plus 1 formal charge. So between the two structures, this one is the dominant one. Okay, go ahead and hit pause and try this practice problem on your own using formal charges to help you pick the valid structure. When you're done, go ahead and unpause and see if you got it right. All right, I'm going to go ahead and go through and write in the formal charges that I calculated for each of these. Using, once again, the equation of valence electrons, minus lines, minus dots for each of the elements. Okay, so this one ends up being -1, +1, 0. This one ends up being 0, +1, -1. This one ends up being -2, 0, 0. This one ends up being -2, +3, and -1. Okay, so in checking our answers here, I'm going to cross off the ones I know for sure cannot be right. So D and C are not valid. D's numbers are all over the place, which would not be very stable. C doesn't add up to 0, right? And the formal charges should always add up to 0. So if they don't, or the charge, but this molecule isn't charged, I know that can't be right. So A and B at least follow in that they're close to 0 and, right, so close to 0, and if you add them together, they both equal 0. So if you notice, the only difference is this one has a -1 on the O, this one has a -1 on the N. So looking back at our rules on formal charge right here, negative charges should reside on the more electronegative atom, and so since oxygen is more electronegative than nitrogen, B is the correct choice. Go ahead and give yourself a smiley face if you got that right. Okay, the next thing to consider when you're looking at a Lewis structure is the ability of a Lewis structure to actually change and rotate as a double bond can be in different places. So what I want you to highlight here is kind of this placement of the double bond, right, being in these different places, right? So it's the same structure, it's just the difference of where that double bond is. And what scientists have found out is they found out that the molecule actually does this and it moves the double bond throughout. The proof behind it, this process is known as resonance, by the way, and the proof that they found is when they've measured the bond length. So let's look at this model here really quick. So when they measured the bond length of a single bond, it was 148 for O to O, and a double bond was 121, okay? But then when they actually measured the ozone molecule, they found both bonds were of equal length, and notice that distance is between the double and the single, right? So it's a little longer than a double bond, a little shorter than a single bond. And the key part is that they were both the same. And so there's this idea of like the molecule actually causes symmetry within itself and moves it around. And since it's moving so rapidly, it appears as if, right, once again, it's everywhere, okay? So the goal here is that if you draw a Lewis structure and you recognize you come into this point of like, oh, I drew my double bonds here, but they could have been down there, and it really looks the same. Once again, I think of mirror images, then you need to indicate that this molecule resonates. This right here, highlight here, is the resonance arrow, and it's what we use to show all the different structures. So technically, we would have to indicate all the structures present to indicate resonance, or the way we're going to do it on our homework is simply by showing, so let me go back to the one we did before, our practice problem. So on here, the last thing I would need to do to finish my Lewis structure is be like, oh, hey, wait, this one can resonate because, once again, it has double bonds here, but they could have been here or here, right? And so to indicate that on my picture, I'm going to draw a double-headed arrow to show like, okay, hey, I know this structure is going to resonate. All right, exceptions to the octet rule. So sometimes we're going to find that things don't turn out as nicely as we thought, and that's why there are exceptions, okay? I'm going to skip this one for now. Let's come to this one with a less than an octet. So I'm going to start the same way we always have before. So boron on the periodic table comes with 3 valence. Fluorine, there's 3 of them, and they each come with 7. Okay, got all those on there. Okay, so then just like we always did, focus on outside, then move inside. So the fluorine, since it has 7 valence, it just needs 1 more to achieve its full shell, which is what the outside ones always are doing, like so. So all of my outside fluorines here. Okay, so all of these have their 8. But this time, if you happen to look in the middle, the boron here only has 2, 4, 6, and so it doesn't have a full shell, but there's really nothing else it can do because it has no more valence electrons to give, and so that is the actual structure. Recognize that by just following the process we've talked about, you get the right answer. Just when you look at it and you're like, oh, this feels a little weird, just know that that's okay. Okay? All right, the next exception we already addressed, but let's put some words to it, and this is the idea of it being hypervalent. So we have one phosphorus and it has 5 valence electrons. And then we got 5 fluorines that are bonding to it. Okay, so in this case, we lose our T shape. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7. So many dots. 1, 2, 3, 4, 5, 6, 7. Okay, so bond each of those one time because fluorine has 7 and just needs 1 more. And we're done. And once again, our center one here, right, has 2, 4, 6, 8, 10. And this is what we call hypervalent, meaning it can hold more than 8. The key thing with this, which is going to link directly to our next exception, is that not all molecules can do this. So they have to have, so if this is my atom, atoms that only have 2 energy levels are too small and they can't hypervalent, okay? So that would be like where boron, if you look at the periodic table, boron, carbon, nitrogen, oxygen, fluorine can't go past 8. They're too small and they don't have room to expand that second energy shell. But everything else, all those atoms found on the 3rd or the 4th, 5th energy level, they all can do it. So this next section comes to the fact of getting on octet, but it always happens with the ones that can't go above 8. Okay, so if I start drawing this just based off how we've learned, we got O, O, O. Okay, they each come with 6. Let's add those on. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, following the patterns we've learned, if I look at the outside ones first, this one has 6, so it's going to want to bond 2 more times. Okay, this one also has 6, so it would want to bond 2 more times. But our center one also has 6, so it only wants to bond 2 times total, right? And so you can see like the center one would be overfilled if we started bonding. I'm going to start with a single bond for each because we know it has to be bonded. Now with these weird ones on your homework, you'll always see that I put in kind of a code that tells you it's going to be weird where it says like, hey, give everyone an octet. Because if we just follow our normal rules, right, this would be kind of as far as we can go because this now gives, for the center one here, 2, 4, 6, 8, and so it can't bond any more times. But both of our outside atoms, right, don't have a full shell yet, right? 2, 4, 6, 7, 2, 4, 6, 7, okay? So we're going to do some weird things to move it around. The key thing with these weird processes, and it's weird, is that we started with 18 electrons total. So we need to make sure our final picture, as we're moving things around, still has 18 electrons total, okay? So here's how I think about it. There's a variety of ways you can think about it, but I think about it, okay, our center one has what it needs, but these 2 ones don't have enough, okay? So we need to find a way to get them more while maintaining the balance of our center, okay? So I'm going to start by, let's create another double bond over here, okay? So that completes this guy, right? So this one now has its 8, okay? Our center one we have now overfilled because we've added an extra bond here, and this one is still lacking. So now what I'm going to do, watch carefully here, okay, the red I'm going to use to cancel, is I'm going to take this little dot and just pass it over here. Because now if you look, we have 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8. So everybody has what they need. They still have 18 electrons total. So once again, this one can be very confusing, but keep in mind it is an exception, not the norm, so try not to get too caught up on it if you understand the general process, okay? All right, last one is when you come across something that has more than one central atom, the skeleton structure is going to be given. So these ones you just add in the dots, 3, 4, and then once again, it's bigger, but just work outside. So we're going to go outside to inside. Whoa, sorry about that. Okay, so hydrogen here just needs 1 bond. So come to the other outside, 1 bond. Now go to the middle. Carbon is going to need 3 more bonds, so that works out great. Do triple there in the middle. All right, so our final structure is like this. All right, that's it. Your homework is homework 2.5 and then some AP classroom quizzes as well. So good luck. Please let me know what questions or things you're still confused about.